grabbing up that.
I want to borrow this for just a minute.
I know, it might take you, well, with the number like 171.
Remember those formulas we took last time to handle certain trig? There, they're right in the center of the screen, right? Aren't those the ones we use when you have a sine squared or a cosine squared and so on? And what's the official title? What does it say on this paper?
This one is power reducing.
Okay, and what did I call him on Monday?
That.
Power reducing.
And you were looking at me like I was crazy. And his sheet, same formulas say half angle.
Yeah. I think that those are not the half angle formulas, though.
You might be
Because I remember half angle formulas,
Right.
and they're an entirely different thing.
Exactly.
Right? Like when you have pi over 8.
Right.
Well, we did that
That's like-
last semester too.
In the book it says half angle formulas.
Yeah, they're just.
The book is wrong.
The book's wrong. Alright.
So
I've been around longer than that book, so it's wrong.
So is it Stephen or Bob that it's messing up?
Who messed up?
Stephen maybe?
James Stewart.
Stewart.
Stewart messed up.
Yeah, what do you expect out of Jimmy Stewart for a math book, right? I know you're not old enough.
He wrote his name bigger than the title of the book.
I would do that.
Terrible.
Okay, did you have enough time to check these? Actually, I don't care what you call them, just so you can use them. But I felt really dumb, like I didn't know what I was talking about, and I thought, oh, I don't have a copy of that sheet here. And now I feel better. Just want you to know I feel better. Okay, then this is the plan for today. In case you're wondering if this class ever has a plan, it actually doesn't, but we fake it. We plan to check the assignment from 7.2. And we introduced a little bit what was going on in 7.3. We're going to finish that off. And then introduce our fourth integration technique, which is called using partial fractions. Another technique, so you kind of see why that works. Okay, but before we move forward into the assignment, just trying to expand your general knowledge a little bit. Here's a common problem you find in a trig or even an algebra class. Pretty tough, isn't it? Find x. And you notice they even made it 3, 4. Except they wrote the 3 sideways. I think that's what throws people off. Okay, here's the solution. Got the problem, find x, right?
Right there.
Very popular.
What can you do? Did they get it right?
I agree.
Which shows you got to be careful when you phrase questions, because you just might get the answer you asked for. Find the x? No, find the numerical value of x and include units. There you go.
No room for error.
Are you going to be doing that on the test?
So you can't be too careful.
Are you going to be doing that on the test?
I try to be really careful so that people, especially like you, that would think of doing it that way won't get away with it. Okay, are there any questions relative to 7.2? Okay, we have one up front here. Go ahead.
19.
19. Okay. 19 coming up. Okay, on problem 19, they're after an indefinite integral. It happens to contain the cosine of x, the sine of twice x, and you know how much it bugs me when they leave out the parenthesis. If the instructor gets bent out of shape when they leave out parentheses here, what does that show? He's over 80. The rest of them don't care. And then, well, you know why I care. Because when I took this class, if I left the parentheses out, 3 points off. And now the books even do it. I tell you, this world is going to. What's ironical though is the calculator won't do it unless you put them in. Go figure. That's the latest technology. So books get sloppy, people get sloppy, and technology says, oh, you better put that in or you're in trouble. Interesting. Okay, you say, I guess he's stalling because he doesn't remember how to do it. You're right. This was a little tactic taught in Education 101. If you don't know what you're doing, get off the subject. Still don't know what you're doing? Say, surely somebody in this class has a plan. I mean, I have one too, but I just don't want to just tell you what it is. Strategy from Education 101. So surely somebody has a plan for doing this one, and you say, Shirley didn't take this class, you're out of luck. Oh, there's one in the back that feels, yeah, the next step is if you prolong it long enough, somebody just might feel sorry for you, or might hope it improves their grade if they speak. Go ahead.
Let's separate it into two integrals.
Oh. Oh, yes. Why didn't I think of that? Says make it that integral plus the integral of, did you do anything to sine 2x or not?
No.
Or didn't you? I just wondered. You didn't? Okay. Then we won't either right away. And I think that's a great move because algebraically it's correct. You could think of this as being the sum of two fractions with a common denominator of sine x. Okay, what's that going to do for me? Make it doable, because the first integral just becomes
Cotangent.
And remember, we have an integration formula for every bare trig function all by itself. But I don't know about that one. Can I make that into a single trig function?
A double angle.
Oh, he said if you change it to 2 sine x cosine x. I think you're going to be okay. All right, so I have to integrate cotangent. Boy, it's been a long time. Did we ever do cotangent? We did, and that went to something with a log in it, I remember.
The log of the absolute value of sine.
That was it. And then technically plus a constant, right? But that's okay, we're going to incorporate it into one big constant in the end anyway. Plus 2, and what's the antiderivative of cosine? No log needed, plus maybe a constant, right? So I'd say the final answer would be something like the natural log of absolute sine x plus twice sine x plus a constant. That seemed to be fairly close, or Bob get something like that?
Yeah, that's the same thing they got.
Okay. So, Luke, did that answer your question?
Yeah.
Did you think to split it in two?
Yeah, I don't know why I lost the plus sign somehow.
Oh,
I don't
okay.
know, so that was just.
You're gonna be all right. Yes.
Will we get marked down if we don't include?
Constants and like intermediate steps. Kind
No. You only get marked down if he's not part of your final answer.
There's no need for you to split them into two separate integrals, right? You can have a sum of integrands.
But you know, if somebody's kind enough to say, I'll give you some things to do, I'm not going to say right away, well, I don't like that, I just want to do it that way. That's very rude. And he's totally correct in what he did. So I'm fine. I just appreciate the fact he agreed to help me out when I was stumped. I'm legitimately stumped on this one because logs are involved. And when you produce logs, stumps often are remaining, right? I mean, it's not a log problem. I don't feel bad about being stumped on that one. When logs aren't involved, I feel kind of weird. Any other questions? 12, okay. Take that one out of view, and we will put in a, you notice I bought some more paper. That's beige. Appreciate it? Is it easier to read than that white stuff? Didn't even notice, okay. 12. That's kind of a nice blah background, makes you sleepy, you know, whatever we can do for you. Okay, number 12 is a definite integral. It goes from 0 to pi over 2, and it's 2 minus the sine of theta quantity squared d theta. Okay, where did you begin? Did you have any ideas?
Just multiply that out and find it.
I think that's not a bad idea, because then you've got sums and differences, and you can integrate them individually. Okay, I like that. So it'd be 4 minus, right, 4 sine theta plus sine squared theta, theta, and then d theta. Okay, now the question is, can I do each of these pieces? I can, except the square doesn't thrill me, because I remember you got to use that power reducing formula, which is often referred to illegitimately as a half angle formula. Okay, what's the antiderivative of 4?
4 theta.
Yeah. What's the antiderivative of 4 sine theta?
Positive.
1.
Yeah, actually minus 4 cosine, but minus minus makes, are you okay with that? All right, that still has to be evaluated from 0 to pi over 4, that's so I don't forget. And then this last one, 4, what do we convert sine squared to make it doable?
1 minus sine, or cosine, I mean, of 2x over 2, yep.
Right? Okay, so we'll take care of this in a moment, but I write it because I don't want to forget that's part of the answer.
Why did that change to pi over 4? Started the problem with pi over 2.
Yeah.
I don't know.
And the last one.
I need glasses, I guess. My eye doctor's no good.
You just got sleepy looking at the
Well, I hope
page.
she's not watching.
Just
She's
thought
gonna
I
be
was
mad.
missing something.
No, I did. It's these glasses.
You're still missing something.
My eye doctor.
Yeah, you're
Um,
still missing.
You mean this one?
Yeah.
Okay. Well, you could have let me get the wrong answer and then laughed at me.
Brought it up.
Yeah, it's pi over 2. I don't know why I changed it to pi over 4. Bad eyes. Okay, this one. Can we go right to the answer? I mean, there's 1/2 I can put out front, right? And then what's the antiderivative of 1?
Theta.
Theta. Minus, and what's the antiderivative of cosine 2 theta? Remember, we did that one so we wouldn't have to,
1/2 sine.
1/2 sine of 2 theta, right? That still has to be evaluated from 0 to pi over 2. Okay, now it's time to evaluate. If I put pi over 2 in, what does this become? This one. Replace theta with pi over 2. 2 pi. Okay, what's the cosine of pi over 2?
1.
It's 0. Okay. Minus, what happens if I put 0 in for theta?
0.
And that'd be plus, what's the cosine of 0? 1. So that becomes 4. Okay, that part's finished. That's applying the fundamental theorem. Okay, 1/2 times. If I put pi over 2 in place of theta, I will get,
Pi over 2.
and I put a big bracket here because 1/2 is times whatever I get. All right, minus. Well, if I put pi over 2 in place of theta right here, and what's the sign of pi? 0. Minus, now put in 0. What's the sign of 0? Oh, that's still 0. So that's not going to contribute much over there, is it? So that's just doing a literal substitution of the limits of integration. So what's the net result? Well, from the first part, I see a 2 pi. I see a minus 4. From the other part, the only contributor is right here, which would be a pi over 4. And now the hardest part of the problem, what's 2 pi plus pi over 4? Let me see, 2 pi used to be 8 pi over 4. Is it still? And 8 pi over 4 plus another pi, that'd be 9 of them. Okay, Bob never got the answer to this one because he can't work the evens, but what was on the answer sheet? That. I guess that sort of verifies it, right? Okay, who asked this question again?
Me.
Which,
I don't know, I don't understand what I was doing wrong. It makes complete sense now.
It's just you can't, it's hard to like think of which things.
Right.
I know, and that's where practice
I think I
comes
was trying
in.
to do a use of when I didn't need to. I think something was staring right at me and I didn't recognize
No,
it.
and that can be very frustrating if it's a test.
Right.
Hopefully, by the time the test rolls around, you'll have some plan in your head for what you're going to do when. One of the assignments connected with the review is going to be a mixture. And one of the things we'll do is we'll say, okay, suppose this problem was on the test. What do you see? What are you going to try? Sometimes there's more than one way to go, but now my approach is the one I like the best is just a plain old U substitution and I'm done. So I always check to see just maybe if that might work first. And you can tell that fairly quickly. You don't even have to write that much down probably. Because whatever you pick for U, you want to make sure in there is also the derivative of U somewhere so that it cancels, remember? And then there's some telltale signs, because if you've got a product and substitution doesn't work, it's always integration by parts. It's these trig ones that we're doing right now that sometimes can be done directly, like the one we just did, and sometimes you need a little substitution. The official trig subsection in 7.3, those are pretty obvious too. There's 3 square root problems that fit. Okay? Sometimes substitution will work, but if it doesn't, then trig sub will. If substitution works and you use trig sub anyway, you'll still get there, which is kind of nice. And then how obvious is integration by partial fractions going to be? Pretty obvious, as you will see. So it's not that hard to discern. Try not to get too nervous, but you'll have a chance to look at a hodgepodge of integrals, and we'll talk about how do I decide on an attack, and what do I look for? You know, we'll try to help you with that a bit before the test. Are there more questions from, okay?
23.
23? Okay. We will, since I buy this paper myself, try to conserve as much as I can. If the college bought it, start a new sheet. No, not really. 23. It's the integral of tangent squared x dx, right?
Oh yeah.
What do I do with that? This is one of those you know, tap yourself on the side of the head when you see it. Say, oh, yes.
Just like,
You got to think which trig integrals are really easy to do. You know, we can do sine, we can do cosine. We can do all the trig functions by themselves, but this is a tangent squared. But there are some squaring trig functions that are easy. Which ones can you integrate directly? Secant squared and cosecant squared. Well, there it is. You see, tangent squared is secant squared minus 1. So this is just a matter of applying one of the Pythagorean identities, because the antiderivative of secant squared is tangent, and the antiderivative of 1 is x. That one's history. And that happens sometimes. And you feel really bad when you didn't see it initially, but don't. It's okay.
I probably sat there and like I don't know, converted tangent to like sine squared x over cosine squared x, and then I
took that so far.
it like I was
Isn't-
nowhere near where I needed.
I didn't try it, but isn't there a power reduction for tangent squared on your little
Yeah.
trig sheet?
Yeah.
Did you try that one?
Probably.
I didn't try to see if
Yeah.
it would work.
Yeah,
I
I
would
did
think
that.
it would, though.
Yeah.
But I think it's a hard way to get to here.
Well, you essentially come up with the same thing if you went with changing tangent x to sine squared x over cosine x, because then you end up changing those into, and then the fractions multiply out the exact same
Okay.
way.
Yep. I think that's the way to fly, though.
Yeah. I don't know why.
That's the shortest way I know. So for what it's worth, there's 23. Just to keep you humble if you missed it. You know, you can't let you get too arrogant. Any other questions from...
56 part C. Oh, sorry.
Oh, go ahead.
56 part C.
56B, D,
C.
C. Okay, I still have a little room on here. 56C. Okay, the original integral is sine x times cosine of x dx. And they said you can do this one if you remember the identity sine 2x equals 2 sine x cosine x. But I don't have 2 sine x cosine x. Well, let's pretend I did. Well, you can't just do that. Well, I'll compensate. If I want to really put an equal sign there and not lie, could do that, right? Now it's still telling the truth? Okay, the reason I did that, and the 1/2 stays, is now convert twice sine x cosine x dx into sine 2x dx. And remember, if I have a sine or cosine of any k times x, you can always do it. Do you remember how it worked?
1 over K.
1 over k, yep. Well, I'd like minus because I want the sign to come out right, but other than that. But the k, of course, is 2, isn't it? So do you see how we ended up with minus 1/4 cosine of 2x plus c? We're good? So that was the plan on that one. Trying to show you that quite often with a trig integral, if you don't happen to see it a certain way, you're not necessarily out of luck, because of all the trig identities around there and relationships, there's usually several approaches, and that's what this thing is trying to show. Here's 56, you can do it 4 different ways. They all work fine. Okay, somebody said which one? D? Or did that go away?
No.
Still check D? Okay. Okay, on 56D, they said do it by parts. Okay. All right, what do you want u to be? Sine or cosine? Sine, okay, I don't think it really matters. And that makes the dv cosine x dx. Okay, to fill in the formula, I need to know what du is. And it will be I also need to know what v is. What's the antiderivative of cosine?
Correct.
Okay, the integral is supposed to equal uv minus the integral of v du. Filling that in, it'd be sine squared x, okay, minus the integral of sine x cosine x dx. And it looks like I'm going around in circles, doesn't it? Except we traveled that road before, and remember it's this integral that's equal to that, right? So I have the identical thing on the right and left side of the equation. So you remember what we did? We added this integral to both sides and got twice the integral of sine x cosine x is equal to sine squared x, and we won't forget our constant. Okay? Then just divide by 2, and you get the 1/2 sine squared x, technically plus c over 2. But we changed c over 2 into c4. And thus the answer we gave you, 1/2 sine squared x plus c4. But you can call the constant whatever you like. Does that answer your question? Remember, these don't happen too often, but if you start seeing yourself getting back to the beginning, that's okay. Then just algebra will finish it off. Yes, sir.
If you take the derivative of those solutions, then you'll get the integrand sine x cosine x, right?
Yep.
So how is it that integrating that will result in answers that vary by a constant? How is that even possible?
Well, all the answers to 56 do differ by a constant, don't you agree?
Yeah, I do. I agree.
Well, what's the derivative of a constant?
0.
So if you differentiate the non-constant portion, it'll always take you back to sine x cosine x dx.
Right. I'm asking the other side of that question. When you integrate it, you get solutions that differ by a constant. So
Yeah.
how is it that when the derivative of a constant is always 0, you integrate 0, and I mean all you have is a constant, but why is the non-constant portion of that solution not equal? I guess sine squared x doesn't equal 1/2 sine squared x, but sine squared x plus c will equal 1/2 sine squared x plus c2, pending you have the right constant. So how, I don't know how else to ask this question.
I'm listening. I'm not sure just what you're getting at yet.
Well, you integrate the function sine x cosine x, and you can integrate it a couple of different ways, and when you integrate it those different ways, you get solutions that vary by a constant.
Right.
But the derivative of a constant is always 0, so you're integrating 0, and you're leaving it in terms of c, which would be any constant. How is it that the non-constant portion of that integrand will integrate differently depending on what method you use? Why is that? That's the question I'm asking you.
Why does it happen?
How is it possible? Yeah,
Well,
either one of those is fine.
it happens because it happens more in trig that this sort of thing comes up, because all the trig functions are related to each other by identities. And maybe the thing to do is, just look at a couple of them to show the equivalence of the answers. The one we just got was 1/2 sine squared x plus c4, right?
Right.
Another answer we got was minus 1/4 cosine of 2x plus a constant, right? And you look at those and say, how can they possibly be the same answer to an integral, only differing by a constant? Well, if you look at the second one and start playing with the trig, one of the identities for cosine of 2x is 1 minus 2 sine squared x, see? Which is the same as minus 1/4 plus 1/2 sine squared x plus c3. Put those two together and you get another constant of some sort, which is c4, and you get the 1/2 sine squared x answer that I started with. So that's why in trig the answers look so much different, but they really aren't different because of the relationships that exist between them.
Right. I can appreciate that. I'm asking a different question. Maybe I'll just wait and see what this class holds.
The numbers is
The non-constant part is what I'm concerned about.
yeah.
But you were wondering how can you get a different non-constant part and it can be the antiderivative of the same thing you started with?
Right. What I'm saying is
It's not different. I just showed you they're all equivalent to each other.
assuming you have the right constant, the non-constant portions of those integrands aren't the same though. That's what I do. It's okay though. I mean, I'm not staying up at night.
Oh, that's a relief. But I might be. Excuse me just a minute. Somebody needs me. Thanks.
I think it's because of the whole numbers on your identity will change that constantly.
I see.
So it'll be different eventually. Depending on the identity you have, your constant will be changed. But yeah.
Not even broadcasting.
No, but you can show her. You can show it to her on YouTube. I love you, mom, or something. Go for it. No,
You should.
my mom doesn't speak English.
Okay, any other questions from,
37.
oh, 37 is out there. Really? I mean, there's some left? Oh. Okay. 37 first.
That's a cheap.
Okay, on problem 37, it's a definite integral. You're going from minus pi over 4 all the way up to, positive pi over 4, all the way up to pi over 2. And it's cotangent to the fifth of phi times cosecant cubed of the same angle phi d phi. I bet you wanted that problem just to know how to pronounce this, right?
That's called, what is it called?
Phi,
How do you spell that?
I just changed all that.
P-H-I,
The answer.
Oh my. Is it P-H-E-E?
You say it out loud.
No.
if you like.
How do you spell it?
P-H-I.
Oh,
It's Greek. Okay, now, when you have a combination like this, we said the key is to kind of take some of it out of there to serve as the derivative of one of the functions that's left. Now I have a fifth power here and I have a cube here, right? I decided to take out one of the cotangents and one of the cosecants. Now, what was my motivation to do that? Well, I know that if I have cosecant squared, I can always convert it to cotangent. So if u stands for cotangent, I can easily get him in terms of u because cotangent squared plus 1 is cosecant squared. So you kind of plan ahead knowing that all the trig has to go if you're going to use substitution. Yes, I did not write it yet, but it's cotangent phi times cosecant of phi d phi. Okay, if you let u equal the cotangent of phi, what's the du going to be? Just what you wanted. But the problem is, I want the derivative to be what I took off. So that's not going to be a good u. You want u to be something that produces this when you do du. I'm just trying to make a point that'll stick, because I've seen that happen a lot. They say, well, I chose this, but it's not working. No, I chose that because it's the derivative of this. Whatever you choose for u, you want that part to be your du. Okay, but I've got some limits of integration, and you know that I like to convert them to u right away so I don't forget. If phi is equal to the pi over 2, does anyone know what cosecant of pi over 2 is? I'll give you a hint, it's 1 over the sine. Everybody knows the sine of pi over 2 is?
What are we looking for?
Just the cosecant of pi over 2.
I know.
So u is 1. Okay, what if phi is equal to the pi over 4? What's the cosecant of pi over 4? Well, the sine is 1 over the square root of 2, sometimes written as square root 2 over 2, but I left it that way so it's clearly cosecant of pi over 4 would be the reciprocal. Okay, therefore, continuing, trying to tell the truth, the new limits of integration have to go from square root of 2 to 1. Cotangent doesn't have a replacement yet, but it's coming soon. What can I replace cosecant squared with? Well, based upon this, u squared. What can I replace the part in the parentheses with? du. Now, as long as I can convert the cotangent into cosecants, they'll all become u's as well. Well, you do have to recall, not necessarily write it down, but cotangent squared of any angle plus 1 is equal to cosecant squared of the same angle. So what would cotangent squared of phi equal?
Should equal cosecant squared minus 1.
Okay. What would cotangent to the fourth of phi equal?
Equal co.
Whatever this is, and then squared, cosecant. Okay, so what can I replace cotangent to the fourth with then? Well, what was plain cosecant?
U squared minus 1.
So it would be u squared minus 1 quantity squared?
Yep.
And the objective was to get everything in the integral in terms of u. So it's square root of 2 to 1. And instead of cotangent to the fourth, I wrote u squared minus 1 quantity squared, and then u squared and then du. And then if I multiply this out correctly, it's something that's fairly easy to do. But I'll keep going as far as you want me to. But usually if I get to that point, people say, I think I can do it. Of course, everybody knows that u squared minus 1, the quantity squared, is u to the fourth minus 1. No, you don't. Should be screaming. Every calculus student always does the square of a binomial correctly. Or otherwise we say there's no hope for you. We send you out of Calvin and let them deal with you. Okay? U to the fourth minus 2u squared plus 1. There, now you should be fine. Distribute the u squared and every piece is easy to integrate. And you have your limits in terms of u, so you can finish it right on the spot. You don't have to convert back to phi. It's okay if you want to convert back to phi, just don't write falsehoods when you say this integral equals this one, because technically
You're getting a number.
I only have equality if the limits are u limits if it's in terms of u. Is that sufficient? Or do you want to check to see if the answer really works? You're supposed to end up with what, 117 over 8? Seems familiar to me. Is that what it is?
No.
No?
That's 4.
Oh, yeah, that's the wrong one. This one was 22 squared root of 2 minus 8 over 105. Yeah, that was it. Are you good? Or do you want more?
65.
Okay. We'll switch to 65. I think I missed somebody's request though. 29?
Yeah.
Then 65. Okay. Okay, on problem 29, I have a tangent to the third of x times the secant x. Okay, what do you think a good u choice would be here? Tangent or secant? Why?
Yeah.
According to who?
Because then you'll get rid of the tangent, and then you'll be left with tangent squared, and you can break that into a secant.
That's exactly right. Did you hear that great answer?
Most of us didn't follow it.
He says because if you do that, and we can put an intermediate in here, he's thinking you'll have a tangent squared left, because if you choose u to be secant, his derivative is going to be secant x tangent x, so one of them is gone. And he said if u represents the secant, tangent squared can easily be converted to secant, so everything can be converted to u, and therefore you're good. Did you want more? We'll keep going if you wish. Well, I think he dozed off on me. Are we okay?
Yeah, we're good.
Who wanted 29?
I did.
Okay. Keep going or
Show it, prove it out.
Sure.
a little further? Okay, now we're going to let u equal secant, which means the du is what I kind of stripped off for that purpose. Okay, so I end up with tangent squared x, right? Du. Now if I can just get tangent squared in terms of u, I'm going to be okay. Well, 1 plus tangent squared is secant squared. So I can replace tangent squared x with secant squared x minus 1, which becomes u squared minus 1, which is quite doable. So the integral becomes 1 of u squared minus 1 du. Which of course is 1/3 u cubed minus u plus c. And then replace all your u's with secants. And you end up with 1/3 secant cubed of x minus secant of x plus c. And we're good. Are you getting a little more of a feel for how the trig works? And kind of what to look for? I will admit that the trig integrals are the hardest ones to make decisions on. I mean, the others are fairly obvious what to do. I mean, parts is parts.
So many routes.
And it's because all the trig is inbred. They're all related to each other. And that's what makes it hard to decide. But the good news is, if they're all related anyway, there's probably usually more than one way to go. One might be a little shorter route, but there's always hope. It's worth trying something because you'll probably get there. And it's not like you're going to maybe do it all in vain, work an hour and not get anywhere. Okay, anything? Oh, we did have 65, right? Right, somebody? Okay. Okay, problem 65 is one of those kind that we did back in Calc 1. They said the velocity function, known as v of t, for a particle moving along a straight line is equal to the sine of omega t times the cosine squared of omega t. That's your velocity function. What they want to know is what's the position function, and they kind of stuck true to form and called it s of t just like they did in Calc 1. Now, how is velocity and position related? See, when you, at the beginning of Calc 1, which of these two functions was always furnished?
S of t.
The position, because to get to the velocity, all you had to do is take a derivative. Then when you hit section 4.9 called antiderivatives, they tended to give you not even the velocity, they'd give you the acceleration function, because by antiderivatives you can get the other two. So to make a long story short, I'm usually better at making a short story long. If you want to find s of t, just find the antiderivative, which is the same as the indefinite integral, of the sine of omega t times the cosine squared of omega t dt. Okay, what's that omega stuff? Constant. Yeah, you got to remember omega is a constant. It could have been 2 or 17 or square root of 18 or whatever, you know. So treat it as if it's a constant. Okay, I do have a sine times cosine squared, right? Which is kind of a trig integral. So the question is, what should I do as far as picking a u? Should it be sine or cosine, and how can one decide? Cosine. Well, if I plan ahead and look at it like this, you'll kind of view it that way. In other words, put the sine in with dt. Then what I have in the parentheses is close to the derivative of plane. And if I let u equal plane cosine, you know, I'll have to adjust some signs, but this is just going to become something involving u squared, see? And I say, I can do that. So if u equals cosine of omega t, then the du will be minus sine of omega t times what? Omega. And then dt, right? So what I kind of stripped off there to serve as the du isn't quite match, but I think I'm good because omega is a constant and minus is like multiplying by minus 1. So how can I review the integral? As a minus maybe omega out front, right? And then I have the, I'm being careful, normally I wouldn't write this much down, but I want you to know what I'm thinking. I goofed though. Okay, but anyway, when I do this particular thing, what's going to happen? In other words, you don't have to think about that, I just want you to know what I'm thinking. What can I replace cosine squared with? That's definitely u squared, right? Okay, based upon this, what is the dt?
That's du over.
It's the du over the minus sine omega t w, right? So what's going to happen?
Signs cancel.
Maybe I'm assuming too much, but du over minus omega sine of omega t is what the dt is, isn't it? Okay, so if I replace dt with this, put that right here, what's going to happen?
It's going to cancel a sign out.
The sine omega t is going to cancel, which is what I wanted. I'm going to get minus 1 over omega, right? And then du left. That's why I had him out front right away. Okay, so now we're back to where we were, but being a little more careful. Well, I think we can go for the antiderivative. We don't need another integral. What's the antiderivative of u squared? So that's where the 1/3 comes from. And then it'd be plus c, right? All right, but they want the final answer not in terms of u, they want it in terms of t. So now we do the substitutions. You can see where you get the minus 1 over 3 omega, right? But what did u stand for? So this would be cosine cubed of t plus c. But that wasn't, Bob's final answer, was it?
It would be omega.
Omega.
Inside of the cosine.
Pardon?
Cosine cubed omega t.
Oh, I forgot my omega. Thank you. But that's not the way Bob wrote the answer. Well, there's the one condition that we haven't read yet,
F of 0.
and it says f of 0 equals 0.
You can find the constant.
Oh.
So that means if I put 0 in place of t, the answer will be 0. See, it means that 0 equals minus 1 over 3 omega times the cosine cubed of omega times 0 plus c. But that's just 0 because omega is a constant. What's the cosine of 0? And 1 cubed is, so you end up with 0 equals minus 1 over 3 omega plus c. So what was your c value? It's just like back in 4.9, they give you what they call an initial value. So you can actually identify the constant.
1 over 3.
Okay, so now going back to here, I see a minus 1 over 3 omega. I see a cosine cubed omega t plus a 1 over 3 omega. And Bob, looking for every last little quarter he can squeeze out of this problem, factored out a 1 over 3 omega. If I know Bob, that's what he'd probably do. And then he'd write 1, see if he can confuse the viewer. Then he'd write minus cosine cubed omega t. Say, there it is. Now, I didn't really check Bob, but having been Bob for quite a while in my day, kind of know how he thinks. And I have a feeling that's what he would do. I'm not sure. Did he do that? Oh, he did do that? What?
He didn't pull it out, he just left everything over.
Oh, he didn't pull it out?
Oh. He did 1 minus cosine cube
Oh, over 3.
all over. Everything all over.
Well, that tricky.
That makes no sense.
Starting to lose faith in my Bob ability, like that. Is that what he did? I'll show you, Bob. Right, this is being recorded. Yes.
Can you, since the argument is the same, since it's omega t for both sine and cosine, can you just replace cosine squared omega t with 1 minus sine squared omega t dt? But then you can multiply that out and you can integrate it into, you take the antiderivative and you get a function that doesn't have any constants except for just the c, you know what I mean? There's no 1 minus, but you feel that that should end up being the same thing.
You could still, well, you're going to get a C no matter how you do it because it's an indefinite integral.
You get a C, but you don't get a loose omega. The only omega that you end up with is inside
That could be.
of a trig argument. So
Could be.
if it's inside of a trig argument, then how will you end up with a solution that has an omega? You see what I'm saying?
Because you'd have to use the chain rule, and that would put one out there maybe to fit.
Well, not to anti-differentiate though. Oh,
Yeah,
oh, you're right.
That comes out.
yeah.
You were right.
He was Bob one day.
Hey, don't mock me.
I won't.
No, not you. He was mocking. He says, come on, he was Bob once. He said it in kind of a derogatory tone, and I'm sorry I admitted I used to be Bob. I just know how they went for every last penny. Well, those were hard days. I was a student. You know what it's like. If you get that ideal job of getting paid to do math, hey, you want it to last. And if you're getting paid by the hour, I know how to make it last. Fix up the answers at the end. And if they bought it, so be it. Besides, isn't Bob's duty to try to get the answer such so that no student would ever get it? So the answer key is worthless? Isn't that the purpose of Bob?
Seems like
Well, it seems like it sometimes. Are there any problems left? There is. 17 is still out there? We must have worked most of them. Wait,
Well, yeah.
maybe I gotta go back to white paper. This isn't working.
There's a couple that we have.
Oh, okay, that's a relief. 17 is cosine squared, tangent cubed, and then dx. You know what bothered me on that one when I saw it? I know how to handle combos of cosine sine. I know how to handle combos of tangent secant and cotangent cosecant, but I don't remember doing a cosine tangent combo. Right?
Revert back to the sine over cosine.
That was my motivation. I say I can do things involving sine and cosine together. So I think I'll make the problem that way and hope that That was just my motivation, because I don't know how to handle this combo. I can do sine cosine combos, I can do tangent secant combos, etc., but not a cosine tangent combo. So let's see what happens. What can I convert tangent cubed into?
Sine cubed over cosine cubed.
Okay.
Okay,
But you can like change the cosine squared to 1 over secant squared.
then what can I do?
Then you substitute cosine for u.
Yeah, he said it becomes this,
A different way to do it when I was helping you. Yeah, like that.
and then he said you could let u equal the cosine, and then his derivative will be sine, and after you take that sine out to serve as the derivative, you have a sine squared which converts to, I think I see a plan here. So u equal to the cosine implies that the du will be minus sine x dx, which means the dx will be du over minus sine x, if you want the algebra to be clear. So you end up with sine cubed x over u times, well, I'll put the minus out front, du over sine x, moving that minus out front, that's part of the dx. And then just like he said, and that's why I say when you do something like this with substitution, some people see further ahead than others, that's fine. You know, write what you see. I can usually follow it okay. So sine squared is, of course, 1 minus the cosine squared of x. I have my u down there, and I have the du. So where does 1 end up? Well, what was u equal to?
Cosine.
You know, one time I was doing this, and I said, what was u equal to? And an English teacher poked her head in the door and said, what were u equal to? And I said, no, that's incorrect. It's what was u equal to.
Environment.
And I stand behind that. What was u equal to is correct. Okay, anyway, 1 minus u squared over u. And then, of course, the old split the fraction trick. And then, of course, everybody knows the antiderivative of 1 over u is natural log of absolute u. And the antiderivative of u, right, 1/2 u squared plus c. Then all you have to do is change the u's back to what?
Back to cosine.
Oh, there it is. Back to cosine. And Bob would probably get rid of the parentheses, and then you should be good. So I have a feeling it's going to end up being the natural log of absolute cosine x plus 1/2 cosine squared x plus c. It's all done. You understand the motivation for the beginning, though, because I think that's the key. I do a lot of talking to myself, and I say self. You start doing that when you don't have any friends. And you start losing friends when you invite them over to your house and you say, who wants to do calculus for fun tonight? Soon disappear. That's okay, it's their loss. But the point is, I say to myself, self, what's bad about this? And I said, oh, there's cosines go with sines when you have products. Tangents go with secants. And so maybe I ought to convert it to one or the other. I have a feeling it would work if I changed this to secant.
That's another way I found out.
I hadn't tried it, but I have a feeling it might. You never know.
it works, because that's the way I did it.
Does it work?
It does.
Okay, now I'm sure it works because he did it that way. Thank you.
No problem.
Okay, do we have any questions left in this 7.2 stuff? I didn't plan on that many questions, but I must have done a bad job Monday. We haven't over here yet, okay? 47. Okay. On number 47, I have an integral that contains 1 minus tangent squared x on top and secant squared x on the bottom, and then dx. Okay, I like to follow up on anything you might have tried. Unless we can see immediately it's going to be a dead end, then we'll explain how we saw that. But did you try something here, or?
I broke it up. I broke the integral up. So
Wow. Couldn't think of anything. He said, how about breaking it in two? We often do that with fractions with a monomial on the bottom, single term. What would it split into?
the integral of cosine squared x minus the integral of tangent squared x over secant squared x.
Okay, he went a little further with his first move, but basically it's this fraction comes from this one minus that one, right? And then you might have heard him say that 1 over secant squared is commonly written as
Cosecant squared x.
cosine squared x.
Oh yeah, that one.
And then the other one, if you think of it as sine squared x over cosine squared x, and you divide by 1 over cosine, which makes it times. Is that okay? I just wanted it to be clear what's happening. Okay, yes, before I get a ton of emails, I know I didn't write my dx, but I ran out of room. I'll try to plan better on the next line. So the net result is cosine squared x minus sine squared x dx. That's what I'm down to. I can do each of these individually by using those power reduction formulas, but I looked at that and said, way back in 1936 when I was taking trig, that was equal to something. Or you swear it's equal to something. And I said, I bet it's even on the pink sheet turned white. Cosine squared minus, I remember there's cosine squared plus, but I know there was something about minus too. Especially if it was cosine squared minus sine squared, and that might save a ton of time.
Oh, wait, cosine
yeah.
2.
Cosine 2.
Of course, that's not helpful unless that's one I can do. And it is. In fact, we talked about a cosine of kx in general. You just do 1 over k, which in this case is 1 over 2. And then the antiderivative of cosine is sine of the same argument, provided you put the minus in there. So I have a feeling one acceptable answer would be minus 1/2 sine of 2x plus c. But I wouldn't expect to see that from Bob, because Bob sees an extra 50 cents lurking here. Because he's thinking sine 2x is that. I don't know, I may be way out in left field on that one.
Yep, I think Bob sees money and not putting in minus signs, it shouldn't be there too.
The minus is bad?
Isn't it?
It is. And so Bob would probably end up with sine x, cosine x plus c. I don't know. But you can stop back here if you want, if you have the right sign. Yeah, I don't know why I put a minus in there. The antiderivative of cosine is positive sine. Is this where Bob
No,
stopped?
Bob stopped up at the half sine 2x.
You did?
Yep.
Ooh, I should give Bob a call and say, you want to make a little more money? I'll split it 50-50 with you.
What, 10 cents?
Okay, any other questions? How are you feeling about trig integrals? Any better or more despair than ever, or you can do it, right?
A lot of trial and error.
Yeah. Yeah, I mean, they're the hardest ones to make a decision on, I agree. But don't forget your trig identities to fix them up, sometimes saves time and all that good stuff. Any questions further? Okay, break time. We'll resume again on this clock at 2 minutes to 7. In real time, it would be 6:01. No, I mean 5:59. Incorrect time.
No,
And we'll see about trig subs.
on Tuesdays or Thursdays, whenever I can. Also, I'm friends with like literally every other person that.
Remind me.
I'm friends with literally. A lot of people say. I'm friends with like almost everyone else from our class last year. I'm friends with Olga and Scott and all of them because there are only like 9 of us left. I mean, how can you not?
Which was hilarious
I
with that
know.
class.
Elaine still talks to me on Facebook all the time. I saw Mike the other day in the middle of the hallway. It seemed like almost everyone.
Message. Just make sure.
Okay. Wrong number.
Sure. I'm not used to seeing it that way. What? Who is this?
I will. It's like even just like looking at stuff also. I own other computers because a lot of times I'm like I look at it way too long and I can't think of any other ways to do anything.
Yeah. Over into the point.
Not really.
You teach me all of your ways.
Don't want to know.
I'm gonna like little Japanese multiplication.
I do, and it was neat, I'm
So-
going to admit, but
That was really cool. Why not save
I'm not
any
arguing.
time?
not always that. To me, that's hard.
For math
Party.
parties. Yep.
Yep.
I go to math parties all the time.
You're a math man. Come on, man. Heard my name, sir.
Scott Langford. Kelly's the one that's.
Right.
Girls are like grouping together. I think it's time too. Is that what's happening?
I don't know if I like that plan.
No.
Where am I gonna sit?
Go one more over. Keep out, throw
This
off
happened to me
everything.
last semester. I got pushed closer and closer and closer to the front.
That's funny.
Fine. Find my trick.
I like it. I like it. I like classes where you sit like way in the back,
Why did
and then
you
the teacher's like,
wrote
I'm
on
gonna
my
be from
paper?
this side of the room, and then all of a sudden you're in the front. I've had that happen a few times. Usually Brian.
Oh.
Well, now you go through screen, so resets.
Ryan sits here, right? Anybody know Ryan?
Here, I got this guy's header.
Brian?
You should just yell at him.
There's two of them.
Oh, there's two, right? Yeah, I know one of them sits here.
One of them sits here. Not
Brian what? What's
Brian
last
what?
name?
Oh, failed.
That's not this one.
No, here's the other one. Oh, look.
I won't. I promise.
I'll just assume this is right. He'll tell me this. Laura uses this right here. Ryan England. Right here. No, you're not.
That's right, Kelly's cleaning up on 20.
There's only one girl less that's gotta be here. AJ. Alexander. Missy and John. John?
Yeah.
So Casey's gotta be here.
Always drop the X. Always do it. Terrible habit. I need to come down and drop an equal sign. I've been doing that for like a year and a half now, all the time. I was
These quizzes aren't in Blackboard yet because it was down when I tried to put them in. So I'll try again tonight or tomorrow morning.
Why would we Skype though? I was just like, be friends. I don't even know. I think I have it. I had it like a year ago, but I don't even know if I used it. Figure out what my account is. You don't use Facebook? That's so strange.
Somebody who understands a little bit more about it.
Knows that crack cocaine is dangerous. And Facebook is similar to that. So he stays
Facebook, social networking is important though. You get like jobs through that and stuff. It's important part of society nowadays.
Okay.
Kinda is.
I have made money
Gilbert's
directly
like my
through
one and
Facebook
only good
use.
friend.
What's that?
I've made money directly through Facebook, like getting jobs and stuff.
Nice, nice. It happens.
Well, money, last semester.
But see, you know what happens? You won't get those jobs when you put those crazy math parties. Facebook profile.
Just makes me look distinguished. Like Tuesday. I
She's
have
breaking out
with
the
my
theta and pi
with my
again.
math mug that I told you about.
A math mug.
I have a math mug. Oh yeah, it's got calculus like equations
It's
all
not
over
cool
it.
though because you don't. They're not holding it up with a calculator.
I know. I have yet to get to that step of coolness.
Link things together, man. That's messed up.
He just remembers everything about me. He could probably tell you my
That
whole
was
life story.
That was yesterday.
Assuming you told me.
Yeah,
So be careful.
yeah.
I'm a little bit worried about how much he knows about me, just because I've.
Not how much he
Yeah.
remembers.
I don't know. I
as,
talked a lot
as you
last
tell
semester.
The guy is a little hard drive.
What can I say?
Careful during break, there's a mic not too far away from you.
He
That
remembers
too.
it all anyway, so.
Or maybe he just reviewed the class. Well, he wasn't here this last
No,
semester.
I used to scare my teachers. I had a German class once, and we took it like a week before she was going over it. So it was a week after she was going over the answers. She didn't give the test back, but she brought an overhead, and she was gonna write down the answers, and it was conjugation. And I was just
For
like,
German?
just the list down. Had it memorized, and she was kind of like,
That's
"What
so
the hell's
weird.
wrong with you?"
What's wrong with this dude?
Memory is
Did
crazy.
he take German last year?
I took 2 years in high school. I took 2 years of French. I took Latin in middle school. I took Spanish in 4th grade.
So how's your French?
I don't really. Russian is my favorite language.
Are you like even more than trilingual?
I don't know.
Oh, okay.
To be.
Well, maybe one and 1/4 lingual, right?
1 and 1/4 lingual.
If
But
that up
multiple
all the-
1/4.
Okay, we're gonna head back to 7.3. Remember, the topic is integration by trig substitution, and this is what we've done so far.
I like it.
We started the introduction. We said trig sub is used when the integrand contains a version of one of the following. You remember what they were? They were all radicals.
Are you writing this over?
One was the square root of a constant squared plus x squared, and another one was square root of a constant squared minus x squared, or the square root of x squared minus some constant squared. I mentioned earlier that when it comes to trig sub, it's fairly obvious when to use it because the integrand has to have some version of one of these. Now, it can be a little bit disguised. I mean, if you had something like the square root of 4r squared minus 9, 4r squared minus 9, I think that would fit one of these. Yeah, I know there's no x, but that's okay because x could have been like 2r. And the a, of course, would be 3. So it's not going to always fit one of these perfectly, but it'll be, like I say, a version of one of these. Okay, we also said don't forget that a u sub may also do the job sometimes much more efficiently. Although I promise you if u sub works, so will trig sub. It just might be a longer way to go. And we had an example like this. So I always check to see if maybe a straight u sub might work. You can see fairly quickly whether it's not going to work or not. Because if u is x squared plus 4, which is the typical choice for u, you just say, is your du in there? Well, I get du would be 2x dx, and the x is right there, so I know it'll cancel and a straight u sub will work. And they do mix a few of those in there just to see if you are being alert. Knowing that if you use the trig sub, you'll be okay anyway. All right, now to the heart of the section, B. What are the basic trigonometric substitutions? Okay, number 1. What do I do with the square root of a squared plus, and I'm going to use u just as a reminder that u could be 2x squared. It might be e to the x squared. It has to be something squared, okay? Well, in order to see what the trig sub is, I think the easiest thing to do is draw this standard little trig picture that you're used to, where this angle is theta. Okay, it's all a matter of where you want to put this, and if it's square root of a squared plus u squared, I'm tempted to put it on the hypotenuse, thinking that the hypotenuse is the sum of the squares of the legs. Well, what would the two legs be if that's the hypotenuse?
A squared and u squared.
Well, a and u.
Right. Oh, yeah, A and u.
And I'm going to put u here and a there. And then the question is, what do you see from that picture? Well, the tangent of theta would be what in that picture?
U over A.
For opposite over adjacent? Which means u itself could be what? A times tangent theta, which isn't too bad. Okay. In this same picture, what is the secant of theta? Well, secant is what? In a right triangle. Hypotenuse over adjacent, if I remember right. Hypotenuse over adjacent. So it'd be the square root of a squared plus u squared over a, wouldn't it? So what does the square root of a squared plus u squared become? A secant theta. Okay, in an integral then, you might have a u. We're definitely going to have one of these, right? But what else is probably in that integral if the variable is u? Probably a du is in there too. What is du going to be?
Gonna be a secant squared of theta.
Okay, so the summary is this. If you ever see a square root of a squared plus u squared, this is just trying to give credibility to where it comes from. If you ever see something like this, if you want to do a trigonometric substitution, what should it be? Well, it's right there. It should be a secant theta. That's the first thing. Any u that might remain in there, any other variable in other words, could get replaced with a tangent theta, and a du that you might have in there is a secant squared theta. So, if you have a problem involving a radical like this, the radical itself gets replaced with a secant theta. Any other u's in that problem get replaced with this, and the du part will get replaced with that. And this, somehow, you want to keep handy so you know exactly what goes where in a given problem. Okay, the others go very similar. Number 2, the one that we're going to look at is when you have this combo, the square root of a squared minus u squared. And again, to see exactly how it all fits, we just draw this little picture where this is theta. Now, if I have the square root of a squared minus u squared, what should go where? Well, the hypotenuse better be what? Can you see that by looking?
It's a squared.
That should be the a, right? And then one of the legs ought to be this, and the other leg ought to be what?
All of it.
See, I want Pythagorean theorem to hold. This has to be on one side, so it should be one of the legs.
Yep.
And if it is, what's the other leg?
The whole thing.
The whole thing. I don't know what you mean.
Everything.
Everything.
Under the radical and the radical.
I thought one of the legs has to be u, when the other leg is
Everything.
Exactly. There you go.
But I already said one leg has to be the square root of a squared minus u squared. What's the other one? You said everything. And the other one was
You
U.
was the simple one, so I thought you did you first.
Now, do you see, I do kind of have a choice here. I could put the square root over here and the u over there. And it'll change the trig sub a little. The reason we go this route is because you get nicer trig functions to work with. Because note the following. What is the sine of theta?
What's it? U over A? Okay.
Which would make u equal to a sine theta. And I like working with sine.
You avoid that.
Otherwise, I have to use some trig function that would work, but it's not quite as nice to work with, that's all. Okay, what is the cosine of theta? in that same picture.
The radical thing over A.
The radical thingy over A. So what can you replace that radical thingy with if it happens in the integrand?
With a cosine of theta.
And if there happens to be a du somewhere, what do you replace it with? Oh, here's your u right above it. Right? The derivative of a sine theta is a cosine theta. So the summary is this. Not that it's not all right there, but this is kind of the bottom line for those who doze off, and you can poke your neighbor if he's sleeping. And that is, when you have a square root of a squared minus u squared combo, what's the trig sub for it? It's a cosine theta. If there's any other u's involved in the problem, replace it with what?
That.
A sine theta. And actually, to get all this stuff, all you really need is this little picture here, because it's all right there. And if there's a du, which there probably is, it'd be also a cosine theta, wouldn't it? So there's the summary of case number 2. Okay, case number 3 is the u squared minus a squared combo. A, of course, is the constant in all of this. So this is the third one, and the final one, u squared minus a squared combo. It all depends on how you want to draw the picture. Well, one has no choice, I think. What should the hypotenuse be, or it's just not going to work out Pythagorean-wise?
U was
U has to go here. It's the legs where I have a choice, right? Well, you tend to get a little nicer functions to work with if the radical goes here this time. And then what's the other leg? Although you could do it the other way, you just don't have as nice a trig function to work with. Okay, the thing to note here is, what is the secant of theta in that picture?
U over A.
The reason I did that is I wanted a replacement for u, which would be a secant theta. Okay, the next one is, what is the tangent of theta in that same picture?
A over the radical, right? Oh, the radical.
Opposite
Adjacent.
over adjacent. Which means I have a nice clean replacement for this in terms of trig. It's going to be a tangent theta. And then from here, if you happen to have a du, what's it going to be? Well, it's the derivative of what you chose for u, which would be a derivative of secant. Okay, just to make it easier to find these back, here's the summary of the last one. And that is, if you ever have a square root of u squared minus a squared, just replace it with a, whatever it is, times the tangent of theta. Any leftover u's that aren't under the radical get replaced with a secant theta. And any du's in the problem get replaced with a secant theta, tangent theta, d theta. And on the last ones I wrote, I noticed I forgot something.
Oh, the
Still have room. Bye, Henry. This one too. I'm going to get my share of emails tonight. Oh well. Okay, we'll put this one in a box as well. And then we'll kind of keep these handy because you just saw them. Did I remove it too quickly? I'm sorry. Because you just saw these for the first time, so I don't expect them to necessarily be in your memory already. But now it's time to see what problems look like, okay? That's all the theory here, showing you where the trig subs come from, okay? All right, and again, lest you get discouraged, the examples I choose are not the simplest ones in there. They tend to be a little more involved because we're together, we can talk about them, okay? And don't be too surprised if a lot of the problems in your assignment tend to be a little more straightforward. That's okay, right? All right, this is C then, checking out what problems look like. And the first one is the integral of the square root of x squared minus 4 all over x to the 4th dx. Yeah, the variable is x, but that's okay. That would be equivalent to the square root of which one in terms of u?
Tangent one.
U squared minus a squared? Yeah, you're a little ahead of me. And what is the a? This is just off to the side, something you would do in your head.
2.
2. Okay? And the u is being played by
X.
x. Okay? All right. So I look back at our list, and right here is the u squared minus a squared choice. So in this particular case, based upon this, the radical will get replaced with what? 2 tangent theta. Now I'm going to be careful on the first one. This will get replaced with 2 tangent theta. That's based upon our findings down here, right? Okay, do I have any bare x's in that problem?
Uh-huh.
And x is like the u here, so every time I see an x, what will I put in?
That right there.
2 secant theta. And is there a dx which is the same as du? Of course, every time you have an integral involving x, you're going to have a dx, so he'll get replaced with, there he is, 2 secant theta tangent theta d theta, right? All right, so this was only on the screen to draw your attention to what went with the radical square root of u squared minus a squared, and there it is, and I got them all written down now. Now we'll put them where you can even see them. So the next step is put those in the integral and hope it happens. But it's not a fun one to do. But it's doable. What do I replace the square root of x squared minus 4 with? Okay. What do I replace x to the 4th with?
That would be
16, 2 to the 4th.
raised them secant.
Secant to the 4th theta. You okay with that? And what do I replace the dx with? 2 secant theta tangent theta d theta. And now what do I hope? Something I can do, right?
Probably combines.
Okay, first thing we do is simplify. Well, here's a 2 in the numerator, and there's a 2 in the...
So that's 4 and then divided by 16.
So I put a 1/4 out front. Are you okay with that? Okay. I have a tangent theta on top and later on another tangent theta, so I'll have
Tangent square.
okay, I have a secant to the 4th on the bottom, but there's a secant theta on top for a total of
3.
secant cubed theta d theta. And there's some irony here, because we just came off a bunch of trig integrals, right? And so we're kind of assuming, I guess, you fell in love with trig integrals, so even if you don't have one, you just do everything you can to make one. No, that's not really the reason. The reason is, if you can convert it to a trig integral, you got lots of things you can do, and maybe there's hope for an answer. Okay, the rest of it is, where do you go from here? It's like we're back in 7.2 again. Any ideas on what to do here?
Multiply the numerator and denominator by cosine cubed theta.
Okay, I could change everything to sine and cosine. I think that would work. And we can do that right away, or we can wait. You want to do it right away? Or would you try to fix up what's here?
You can fix that.
That's
I mean, tangent squared is
1 minus.
secant squared theta minus 1, isn't it?
Yes, you're right.
But it's not going to matter, because I'm going to want to go to sine and cosine eventually anyway. And whether you do it right away or wait, one might save you some steps or not. Now, actually, I wouldn't have written that step. I would have gone right to this one, because we're kind of planning ahead. Because remember how we split fractions? And secant squared over secant cubed is,
1 over secant.
and I wouldn't even write this step, but I'm being careful. Minus 1 over secant cubed theta, right? That's d theta. Okay, now it's real easy to convert to cosines, right? Because what's 1 over secant? Yeah, it's cosine theta. What would 1 over secant cubed be? Okay, if I had a problem like this in section 7.2, guess what we probably would have done? There's a minus sign. It's not multiplication, unfortunately.
Wait, what are we doing?
We'd probably factor. What would be our motivation to factor? The fact that I get this.
And then,
And that's kind of good news, because what's 1 minus cosine squared?
Sine squared.
Yep. Now it looks like one of those beginning integrals from 7.2. And you remember how we handled it? What did we let our u equal?
cosine. No, sine.
Actually, we didn't. We let the u equal sine theta. Because then our du is what? Cosine theta d theta. So what does this become? Well, every time I see a sine, I'll put u in there.
It becomes u squared.
And every time I see a cosine theta d theta, I'll put... That wasn't too bad, was it? The problem is, the end is so easily seen, but we're not nearly there yet. Why not? Well, what's the antiderivative first?
1/3. Third.
So the answer is 1/12 u cubed plus c. Now it's that same old thing again. I have nothing against you, I just don't like you. Because the original problem had what in it?
Yep.
Well, if you can think back that far. Wow, look at that. Oh, the original one had x, so you can't quit until the final answer has x. And you say, I don't even want to do this assignment. Look at this. This is terrible. Well, I just tried to pick one that would be one of the worst ones you could encounter in the assignment and show you it's very doable. So you're supposed to be inspired, saying, oh, if I can see this one, I can do anything in the assignment. It never works, but that's the theory. Okay. All right, so what's the first thing? We'll have to do a double substitution. What did U stand for? It's still here. It's a sine theta, so it's 1/12 sine cubed theta plus C, right? Okay, but what can I replace sine of theta with? Well, if I go way, way back, and I can just grab that paper where the problem started and put it right here. I don't have anything involving sine anywhere. I got this square root in terms of tangent, and I have this one in terms of secant, but I don't have anything with sine in it. Well, that's why we drew those little pictures for you. Because that'll help you to find any trig function you might end up with at the end. Now, in this particular one, and we'll bring that back into sight. Here it is. This was the one where you had a u squared minus a squared. In our case, it was x squared minus 4. So remember how the u, which is x for us, goes on the hypotenuse. We put the radical here, and then the a went there. Okay, let's fill it in for our particular situation. What's on the hypotenuse? U was there, okay? What did U stand for? Way at the beginning, X. I probably shouldn't have used U again at the end. I probably should have used omega or something. Okay, what was on the leg to the opposite of the angle? Remember what we put there? The radical, which would be x squared minus 4. And what was on the other leg? 2. Why did I want that picture? Because I have to convert sine cubed into x language. And it's real easy with that picture. It's 1/12. What's sine in that picture? Opposite over hypotenuse. So it's square root of x squared minus 4 over x. And that would be cubed plus c, and I'm finally done. I'm sure Bob is having so much fun he'd want to try to fix that up, but I'm happy. They give you a little bit of a feeling how the trig sub works, and at the end you got a little ways to go to get back to the original language of the problem. Did it make sense? Well, if you did your assignment 7.2, it's just a matter of picking the right substitution and then hope it turns into a trig integral you can handle. And if it does, you end up with a trig answer which can be converted back to the original language using that little triangle. Yes, sir?
Way back when we had the integral of cosine theta minus cosine cube theta.
Yep.
We have just integrated that and then solved or then put.
I can do cosine. What about cosine cubed?
Oh, right.
I split it because I wasn't sure how to handle a cosine cube.
Yep.
Now, another way you could have skipped all that was just to turn it into sine and cosine at the beginning.
Which is kind of what I said, but I know you wanted to
you
take
actually
the long
go
way
from
around
there
it to
to-
multiply.
I mean, skip this stuff in here.
Yeah.
Yeah, you can just turn those.
I don't know if it would have been faster to get there or not. Maybe. I'm fine with that. I said that right away. I said you can convert to sine and cosine right away, or you can play with the tangent and secant and convert later. That's up to you. Whatever you feel more comfortable with. That's immaterial to me. Okay? Just so eventually you get down to this point. So what they're saying is, I don't know, I'm not thrilled with working with tangents and secants. I'm a sine cosine person, so I want to convert right away because I feel better. Fine. It's not necessarily going to get you to the point you want to be faster. Now it looked like mine was really slow because I wrote 2 steps I wouldn't ordinarily write down that I would do in my head, but that's okay. But you can't read my mind. I tend to write down what I'm thinking.
It was only 2 steps, huh?
Yes, sir.
I wasn't raising my hand, sorry.
Oh, you're just stretching, okay. Are you ready for example number 2? Have you,
I get what you mean. Yeah, I get what you mean.
are you okay?
End up with that right there.
That was awful.
Yeah, that we
Yeah,
end up with that.
I warned you.
Instead of having to switch.
I picked the problem for that reason, just to show you how these things can go on and on. I don't plan on them all being that way, so I don't want you to be disappointed if they're a little shorter. Okay?
But yeah, usually it's
Right? Okay, example number 2. This is one, how do you handle it if it's a definite integral? Problem number 2 is a definite integral. It happens to be the integral from 0 to 2 of dx over the square root of x squared plus 4. And again, the presence of that radical is trying to tell you trig sub. Now right away I thought maybe this is easy. If I let u equal x squared plus 4, then maybe I can get done really fast using a u sub. Trouble is, if I let u equal x squared plus 4, I need a what? An x at least, because the du is going to contain a 2x and he's just not there. So I'd say probably trig sub is my only choice. Okay, the next move is what trig sub should I use? And we bring this onto the screen right here. It says when you have an a squared plus u squared, so right here, what's the a going to be? I mean, to match my formula. And what is the u going to be? X again. And it says when you have that u squared plus a squared combo, go to secant for the radical, tangent for the u, and of course a secant squared for the du. And I remove this and we'll fill it in for what we need. And the answer is no, you don't have to write this down. I'm just doing that in case you look back and wonder where did he get that stuff from. So based upon our formula, the square root of x squared plus 4 will get replaced with a secant theta. Any x's left over, which there aren't any, but just in case there were, will get replaced with 2 tangent theta. The dx is always there, and he'll get replaced with 2 secant squared theta d theta. But you know me, when I write equals, I don't want to lie. This is going to be turned into a theta integral. So I continue on like is normal and say if x is the upper limit 2, then what does that make for theta? Well, x is 2 tangent theta, right? If x is 2, then tangent theta will be what? I think you can do that in 1, won't it? And the tangent of what angle is 1? Now some people really rebel at this point and say, I'm not going to substitute till I turn it all back into x's. Well, you saw in the last problem it might be quite a process to get it back in terms of x. This says when I'm in terms of theta, I can plug in the numbers and be done. So it's your call. Just don't write equalities which are not true. Well, what would you do if you waited till the end? You leave the limits off. Then write your equals, and then at the very end you say, therefore, if x equals this, then that's what you get. Okay, but I've started on this path. What if x is 0? Then using this middle one here that I just circled, tangent of theta will also be 0. Tangent of what is 0? Yep. So it's not too bad. I don't know how you feel about trig, but I don't mind a 0 to pi over 4. What do I replace dx with? Right. Just to the right. 2 secant squared theta d theta. What do I replace radical x squared plus 4 with? Okay. How does this one look compared to the one we just did? Is that more up your alley? Whatever that means. That means more to your liking. Sorry, that's an old 1918 term. Your past tends to rise sometimes when you're nervous in front of a group.
What was the original limit from 0 to what?
2. Sorry.
Yeah, I don't know.
Okay, simplifying. What does that integrand become?
Secant?
Plain secant theta d theta. Oh, is that good news? Yep, any plane trig function is doable. It's just a matter of remembering which natural log it goes to. You remember the natural log of secant, what he turned into? I mean the antiderivative of secant?
Oh, sine, or something. Yeah, that one.
Yep.
Yeah, clearly that's what the antiderivative of secant was. And still is. So I have to take the natural log of secant pi over 4 plus tangent pi over 4 and subtract from it the natural log of the secant of 0, minus the tangent of 0. Did it again. Okay, do you remember what the secant of pi over 4 is?
Root 2.
Yes. Do you remember what the tangent of pi over 4 was? Do you remember what the secant of 0 is? Right. What's the tangent of 0? Right. Hey, what do I have here? Natural log of, there, 1. What's the natural log of 1? So what's the final answer? And since this is a positive number, I don't need the absolute value. And that is a numerical answer. It's called the natural log of the square root of 2 plus 1. Final answer to the value of that integral. Look at that. All here without scrolling.
Definite
bad.
seem easier then.
Pardon?
Definite integrals in this way seem a little bit easier than shorter.
Well, the problem was rigged. So don't count on it.
Right.
Yeah, like we went from
But if you change your limits, you have definitely a lot less
Right.
back substituting to do. But that's a personal preference. I always have a few students that just don't like my new limits, so they just integrate this as if it was not definite, and then forget it was definite at the end, and then forget to finish it.
get points.
But you can do it that way if you don't forget at the end. Any other questions on second example? Okay, now you're ready for another nasty one. Oh, okay. Here's number 3. It's an indefinite integral. It happens to be the square root of 1 minus 9x squared dx. Now I want it to match one of these. Because those are the ones I have trig subs for. I actually would use. Which one has the greatest potential?
Middle one?
I'd go for this one. If I do, what's the A going to be?
Yeah, it's got to be 1.
And the 3x.
What is the U going to be? These should have been U's.
3x.
Yep. Okay. All right. So if I let A equal 1 and U equal 3x, then I do have a combo of A squared minus U squared. Okay, I gotta find that one. Let me see. Ah, here he is. Here's the old a squared minus u squared combo. And the radical becomes
Cosine.
a cosine theta. The u becomes a sine theta, and the du a cosine theta d theta. Okay, hoping you can remember that. We'll convert it to this problem. First of all, the radical 1 minus 9x squared. Now remember, it's a cosine theta. What's a?
1.
So it's going to be 1
Cosine.
cosine theta. But don't forget this, okay? U is assumed to be 3x here. All right, in the next move, well, the u, which is 3x, has to be what? A sine theta. And finally, the du, which is really the derivative of 3x, right? Has to equal what?
Cosine theta.
D theta. Now, where you have to be a little careful here is in the problem, I don't have the derivative of 3x, I have the derivative of x. So, therefore, what do I have to do? Now, to compensate when I fill this in, well, let's keep going. The 1 minus 9x squared, what can it be replaced with?
Cosine theta.
Okay. That's fine. What about the dx? Well, d of 3x is this, so what would dx be?
Was it 1/3?
Yeah. See, dx would just be 1/3 of that. Okay with that? So therefore, because remember when you do this, it's going to be the derivative of what's inside at the end, which is 3. So it'd be 3 dx, which is 1/3. So I'm going to put the 1/3 out here, and the dx can get replaced with cosine theta d theta. So you got to get to this point somehow. Now what some people do is a u substitution first, let u equal 3x, and then they right back here they say du is 3 dx. Then dx is du over 3, like the good old days. And feel free to do that if it makes you more comfortable where the 1/3 comes from. Okay? The dx, which is I have to replace, is 1/3 the du. And the du is this. So 1/3 of that is what the dx is. Do I have something that's doable? Yep. I think we did those kind in 7.2. So now it's just a matter of seeing what happens. Do you recall how that went in 7.2? What we did to handle this? We used the power reduction formula, which has been falsely accused of being the half angle formula. How are you ever going to forget the power reduction after that, right? Anyway, yeah, it's 1 plus or minus. Plus for cosine. But it's okay because it's on your sheet. You shouldn't get it wrong. The cosine of twice theta over 2 d theta. Gotta keep this separated. Okay, that'd probably be 1/6 times the integral of 1 plus cosine 2 theta d theta. And I'm ready to integrate. Don't forget the 1/6 times, what's the antiderivative of 1 with respect to theta? Theta. And what's the antiderivative of cosine 2 theta? Yeah, you got that down, right? 1/2 sine 2 theta. Then, of course, maybe some constant on the end. So what does it take to get the final answer? Just get everything back in terms of x, right? Okay. Here's theta. Back here over to the right and up a little. It says sine of theta is 3x, right? Or u, whatever the case may be. I want x though. So sine of theta is 3x. What's theta? Do you remember how to convert that? This has not happened before today. If sine theta is 3x, then what's theta? Yeah. Remember this? If sine theta equals 3x, then theta is the inverse sine of 3x. Remember those days? A long time ago. Okay, the next one isn't quite as bad. Plus 1/2. And again, I don't know what sine 2 theta is, and that's why I'm converting it to 2 sine theta cosine theta. Just being careful, and so you don't wonder where the 2's went. Okay, what's sine of theta again? That's right up here. It's still on the screen. So I see this turning into a 1/6. It's inverse sine of 3x plus, I'll replace sine theta with 3x. And what about cosine theta? If sine theta is 3x, what's cosine? Well, I think it's up here. See it? It's not even off the screen. It's the square root of 1 minus 9x squared. And that could be the final answer right there, provided you put your c on the end. What do you think Bob's going to do? Not much, but he can't resist getting rid of the brackets. But I'm thrilled if you get this. I'm just as thrilled if you get this, but not really more thrilled, because that was not a big move. No extra points for getting rid of the brackets. That's too Mickey Mouse for a move for extra credit. Any questions on that one? So you had to adjust the 9x squared. Okay, our last example. You can't see right away that it's even going to fit. But this does happen occasionally. I wish to integrate the square root of 5 plus 4x minus x squared. The only thing that might suggest that this is a trig sub is the radical. But when I look at that radical, it doesn't fit anything that I can trig sub for. So guess what you do? You do some algebra to make it look like something you can do a trig sub on. Now remember, for a trig sub, you either have to have the sum or difference of two squares, right? And way back in algebra, you did this move which you knew was worthless. It was just there to harass the poor algebra students. It was called completing the square. Remember that? That's what I have to do here. Okay, so this is the integral of the square root of 5 minus x squared minus 4x dx. This is what's called being very careful. Are you okay with that move? It's quite a move. I kept the 5, I put a minus sign and converted this to x squared minus 4x in parentheses. Actually, that's good algebra, sort of. Yes? No? Why did I do that? Well, to complete the square, I like the square term to be positive because it's easier for me. That's why I did it. It's easier for me to complete the square if the x squared is positive. Okay, to make a perfect square out of this part in the parenthesis, what would I have to add? Do you remember those days? I want to make this into a perfect square. Remember, it's half the coefficient of x and then square it?
Those 2.
You say, you change the problem. You can't just add 4. Yes, I can if I later on subtract it off. But be careful. Did I really add 4 here? Why not? Because it's in the parenthesis. I really subtracted a 4, technically. So to compensate for it, I'd have to do that, wouldn't I? Now you can see that this problem, like most things in a math class, is what? Rigged. Because 5 plus 4 just happens to be 9. Isn't that nice? And what is this a perfect square of? Okay, now do I have something that matches one of the trig sub?
Yep.
So they complete the square to get a squared minus u squared. Okay, what's playing the role of u here then?
X minus 2.
That means if I need a du, it's going to be the same as dx, right? Correct? If u is x minus 2, then the du is just plain dx. What's playing the role of a here?
3.
3. So under this combo, this becomes the integral of the square root of 3 squared minus u squared, doesn't it? Du? With these substitutions? Just trying to make it match directly one of the 3 combos we have that lead to a trig sub. So if I let u equal x minus 2, then this integral becomes that one. Okay, now I gotta look which one. It happens to be lying on top. And there's the one where you have an a squared minus u squared. So what's the combo? The radical becomes a cosine theta, any u's left over become a sine theta, etc. Okay? So I'm going to let the radical 9 minus u squared be a cosine theta. If there's any other u's involved, it'll be a sine theta. And for the du, I go with the derivative 3 cosine theta d theta. Okay, so then this integral is truly equal to, replace the radical with what? 3 cosine theta. Replace the du with
Cosine d.
and I have 9 times the integral of cosine squared theta d theta. Now that was sort of deliberate because I thought I just might be running out of time at this point. Actually, we're not doing too badly, but doesn't this integral look familiar? We just did it, didn't we? Okay, so if you look back at problem 3, you remember, and I know this is dangerous, but do you remember what I can turn this cosine squared theta into once it's all been integrated?
1 plus cosine of
Or is that too dangerous?
I
half angle stuff.
The power reduction.
So it's going to be 1/2 times the quantity
So it's, I put that out there then.
times the quantity. I don't know how far into it you want to go. Theta plus.
The answer.
Oh.
Oh, that far?
Well, that would be the inverse sine of.
Not that far. No, the end of the integral in terms of theta.
Right.
In other words, remember cosine squared was the same as 1 plus cosine 2 theta over 2. So the 1/2 went out front, and then what was left, if you look at the last problem, was theta plus 1/2 sine 2 theta. And I guess we could have gone one step further, because this would become 9/2 times the integral, or times the quantity theta plus, remember how we replaced this with 2 sine cosine? So it just became sine theta cosine theta. We'll say C, in case you look back and wonder what are we doing, see example 3. Just copying what we got from there. Okay, we're finished when we convert everything back to what?
X.
To x, okay. All right. Still sort of on the screen is this stuff here, right? I have theta, and right here I have u equals 3 sine theta. So u over 3 would be sine theta, wouldn't it?
R cosine.
So this would be inverse sine of u over 3. Are you okay with that? That's what theta would be, because sine theta is u over 3. That comes right from this substitution back there. Okay, what do I put in for sine theta? U over 3. What do I put in for cosine theta? Well, if you look near the top of the screen, 3 cosine theta is this, so cosine theta would be the square root of 9 minus u squared over 3. Am I finished?
Oh.
No, all the u's have to be replaced with what?
X.
Yeah, if I scroll up a little bit here. There it is. What did u stand for originally?
X2 something.
X minus 2. See that? It's right near the top of the screen. So every u gets replaced with x minus 2 and I'm done. So it's 9/2 inverse sine of x minus 2 over 3 plus x minus 2 over, let's make it 9, times the square root of what? Well, if you were alert and I replace u with x minus 2, this is going to be the original radical I started with, and that's what Bob's going to do.
Oh, you pulled out the 1/3 out of the next one?
Yeah, I moved it over here to make 9. And you see that this radical right here is just going to go back to the original every time? And Bob's going to write it that way. What else will Bob do, which we're not going to do? Distribute the 9/2 because he can't wait to cancel it with that one there and all that good stuff. What I don't have time to do, which I was hoping I could do, is grab one like this, put it in the calculator, and see if it will stump it or not. And if it doesn't stump it, see if it's anywhere close to what we have here so I can even recognize I got it right. But you can try that. Your assignment, of course, is 7.3. And I didn't get a chance to introduce 7.4, but that's life. So your assignment for Monday, 7.3. Have fun putting together some trig subs. Have more than you can eat, invite your friends over.
Why are you always
I do too.
Really make sure.
Okay, I guess that's it. So if you want to pack up, that would be fine.
I've never thought that about any of them. I don't even know if I have my if I know what my spike unit is. But it looks like my battery is sad. I get to go walk on my phone.
Exciting.
I know.
Exhilarating.
I live just close enough where I feel too bad to pay the money to park every day, but just far enough away where I hate myself every day walking home. Your half hour will be now.
Well, you have to remember, roads are so. That's always something to look forward to. Fun on your exhilarating walk.
It's about to be so cool outside.
Almost zero tonight.
It was like 11 when I think I left.
It's been a long time since we got that one. But it had to happen, I guess. Okay, where's your hat? You can go up there without a hat. What?
I have all of them paired.
Oh, okay.
See you Monday.
Okay.